Welcome to our today's class. Today we have further mathematics, and the topic we are looking at is limit and continuity. So let's first of all understand what a limit is. A limit is defined as the behavior of a function as it approaches a specific value. In a limit, from this question, s is approaching 0, and second question, h is approaching 0. So, but there are some basic rules in limits and some special limits. One of the basic rules in limits is that it cannot be 0 at the same time. If it's 0, this expression is indeterminate. Indeterminate. It cannot be determined. So our denominator must not be 0 anytime you are dealing with a limit. Because if it happens to be 0, that means the expression is indeterminate. In that case, we need to simplify the expression to make sure our denominator is not 0. We also have another special limit, sin x over x. As s approaches 0, the value is also 1. The value is 1, where you have this is special limits. They call special limits. Special s is approach 0, sin s over s is 1, can be done through a series called Maclaurin series or Taylor series. That is a little bit of advanced maths. If you approach that method, you will see at the end of the day, the value of x is 1. So with that, let's take our question. So as s approaches 0 in question 1, means that anytime I see s, I should put 0. If that should happen, this one will give us root 1 plus 0 minus 1 over 0. So since we're having denominator as 0, it disqualifies the solution already. Our denominator can be 0. So with that, I will manipulate this expression to see how my denominator is not 0. So how do I do that? I will rationalize the numerator. So let's rationalize the numerator and see what we. So let us rationalize the numerator. Let's see what we have. By rationalizing the numerator, I will look for the conjugate of this expression. That is, you need the idea of surd. The conjugate of this will be a positive value. X tends to 0. Root 1 plus x minus 1 over x. So you multiply with the conjugate. This will give me root 1 plus x. So instead of having minus now, we are now having plus 1 over root 1 plus x plus 1. So the conjugate of root s plus 1 plus s minus 1 is same thing as root 1 plus s plus 1. So minus becomes plus. That we have by doing so, we rationalize. So use that conjugate to multiply the numerator and the denominator. So if I should go by that, I'm having lim x tends to 0. So let's bracket this 2. I'm having root 1 plus x minus 1, root 1 plus x plus 1 over, let's multiply this 2, x into root 1 plus x plus 1. So we should take into account laws of surd. If you have root m times root m is simply n. Anytime you are multiplying two equal surd, the value is just what you have inside. The surd we have to leave. So if I should apply this knowledge in dealing with this, I'm having lim x tends to 0. So if you just multiply this, they are the same according to this law of surd. I'm just left with 1 plus x. If root 1 plus x multiply 1, I'll be having root 1 plus x. Minus 1 multiply this, I'm having minus root 1 plus x. Minus 1 multiply plus 1, that will give us minus 1. X into root 1 plus x plus 1. So let's look at the numerator critically. By adding those we can add and subtracting those we can subtract. So 1 and minus 1 is 0. 1 plus root x minus root of 1 plus x is 0. So what are we left with? I'm left with lim x tends to 0. We are left with x as the numerator over x plus 1. So by looking at this expression, you agree with me, x can cancel x. So this one now implies lim x tends to 0, 1 over root 1 plus x plus 1. Let's substitute s now as 0 because s approach 0. If you do that, this will give us 1 over root 1 plus 0 plus 1, which is 1 over root 1 plus 0 is 1 plus 1, which is 1 over, square root of 1 is 1 plus 1. Our answer is 1 over 2. So this is how to simplify the limit. So make sure your denominator is never 0. If it happens to be like that, manipulate the expression either by factorizing, rationalizing, or applying the principles of special limits. Either of them will serve. So if you have any area of observation, please don't forget to share it in the comment section. Thank you. See you next time. The two questions we wrote earlier. The question say lim h approach 0, 2 cos in open bracket s plus h over 2 sine h over 2 everything divided by h. Like I said, if you substitute h as 0, the denominator is already 0. That means it's a determinant. We can't find the solution. So with that, I need to manipulate this to ensure my denominator is not 0. And since we're having sign in the expression, I need to apply the concept of special limit that says sine x over x as the limit of s approach 0, the value is 1. They call this a special limit. And this value can actually be proven or obtained if you apply the concept of Maclaurin series or Taylor series. That's a little bit of advanced mathematics. So what is this special limit trying to tell us? It's trying to tell us that anytime you see a sign, and then the variable after the sign must be equal to the denominator. That's the only condition. The limit of this can be 1. Another case, I have lim x tends to 0 of sine 2x over x. You can see the variable after the sign is not equal to what we have in the denominator. So I can say this follows the principles of special limit until I make sure I add 2 here. By introducing this 2, which is not here originally, that means I will introduce an equal number, I can remove it. So you can see now what we have here is same thing as what we have here. Therefore, this whole expression, according to special limits, is 1. So we are simply having 2 times of 1, which is 2. So let's apply this knowledge in dealing with this question. So what we have is 2 cos, open bracket, s plus h over 2 sine h over 2. So let's simplify what we have. We have a lim h tends to 0, 2 cos s plus h over 2 sine h over 2 over h. So I can write this as lim h tends to 0, 2 cos s plus h over 2 times sine h over 2 over h. So here is yet to satisfy the condition for special limits. Why is it so? Like we discussed earlier, whatever I have after the sign must be equal to whatever I have in denominator. After the sign is 2x, what I have in the denominator is 2x. So if we bring that knowledge here, what I have here is h over 2. Here is yet to be h over 2. So if I'm introducing here as over 2, that means I will multiply with an equal variable, just as we did here. I need to multiply with an equal variable to ensure the 2 I'm introducing is not having any effect on the original question. Lim h tends to 0, 2 cos s plus h over 2 dot or times sine h over 2. So I'm introducing 2. That means I will multiply with an equal variable. Nothing changed. The reason I'm doing that, I want to make sure whatever I have after the sign is equal to what I have in the denominator. That's the only way it can follow the concept of special limits. So you can see now, what I have here is what I have here. So by h approaching 0, this whole expression is applying the concept of special limit now. This whole expression here is equal to 1. Why is it so? According to special limits, what I have after the sign must be equal to what I have in the denominator. With that, it becomes 1. So this will give us lim h tends to 0, 2 cos s plus h over 2 dot lim h over 2 h over 2. A special limit. This whole expression is to 1. So if I put my h approaching 0, this will give us 2 cos x plus 0 over 2 is simply 1 times, I'm still left with 1 over 2. So this will give us 2 cos x plus 0 over 2 is 0 times 1 over 2. So this 2 can remove this 2. I'm left with cos x times 1, and one answer is cos x. So this is how to solve a limit. Make sure your denominator is never 0. Please, if you like what you are watching, subscribe to it, share the video, and press your notification button. Hope to see you next time. Thank you.